Last class we talked about semiconductors. We got an introduction to semiconductors. So what did we learn? I'm waiting. What did y'all learn? So what is a semiconductor? Got 4 electrons in the valence shell, right? We classify elements as conductors or atoms as conductors if they have 3 or less. 1, 2, 3. We classify insulators if they have 5, 6, 7, and 8 in the outer shell. And a semiconductor is classified as having 4 in the valence shell, right? And the 2 predominant semiconductors that we use, that we're going to discuss, even though there's more, we'll basically start off using silicon and germanium. So is a semiconductor a conductor? No. Is it an insulator? No. So basically it's kind of like a resistor. In fact, on a lot of integrated circuits where the entire circuit is integrated on a single wafer, that's what the resistors are made of. They're made of nothing but silicon. And depending on the thickness of it and how it's laid out would depend on the actual resistance of the silicon. So it does conduct a current, but it doesn't conduct a current very well. Everybody okay? So what happens to be able to control this conduction or change the conduction characteristics, what we do is we start doing what's in chapter 3. So the term semiconductor in electronics does not mean a pure semiconductor. When we use semiconductors, the term semiconductors in electronics, we mean a semiconductor that has been deliberately, that we've introduced other atoms into the lattice, into the crystal to change the conduction characteristics of the silicon. So what we do is we take and form what's referred to as a p-n junction. And something's missing here that I just did. So we have 2 types of materials. What we do is, so I don't know what happened unless I didn't save it. We're going to pick up a term called doping. In semiconductors, doping is when we deliberately enter other atoms into the semiconductor to change its conducting characteristics. Now what we do is the atoms that we introduce into them, one of them we refer to as a trivalent. So a trivalent atom is defined as an atom that has 3 valence electrons. Valent. And then we have another element that we refer to as a pentavalent. What do you think? What would you think about that one? Penta meaning 5. So these would have 5 valence electrons. And these are deliberately introduced into the crystal, the silicon crystal, the intrinsic crystal, to change the conduction characteristics of the semiconductor. So if we introduce a trivalent, what we end up with is this. We end up with maybe 2 electrons right here, 2 electrons right there, 2 electrons right here, and we end up 1 right there. And what's it trying to get to be what we call balance? It's trying to get 8. So what this does, it produces an absence of an electron in the absence of the electron, which we refer to as a hole. Now, the material is still not charged because the number of protons in the crystal and the number of electrons in the crystal still match. And as long as your electrons and your protons match in a crystal, then the crystal has no charge. Y'all understand? So it's uncharged. So what I end up with is I end up with a bunch of holes floating around here. Now, as soon as an electron falls into the hole, then we have an ion, right? You understand? Then it wants to kick it out. So what happens now is we come over here and put a polarity across this thing. Now the resistance go down. In fact, we might have to put a resistor. And what happens is these holes flow from where? The holes are flowing from negative to positive. I'm sorry, from positive to negative. And of course, when it hits these wires right here, it starts filling in electrons, and then other holes flow in from this side over there. That's what we got to understand. In the conductors and in the source, we have both holes flowing and electrons flowing. That's what we talked about last class, right? So what we say in one that's been doped in trivalent, we refer to this as P material. Even though it don't have a P charge, it's called a P material, and we'll find out later on. And we call it the majority carriers. So the majority carriers in P material is what we call holes. Everybody follow this up on? Pretty interesting, right? So inside the P material, 99.99% of the current flow is holes. The electrons are not really doing it. Y'all understand? Which is pretty neat. Now, we do have what they call some minority carriers. We call it intrinsic semiconductors. Intrinsic means, so you'll see that term used all the time, but intrinsic means a pure semiconductor. And it's highly unlikely that we'll ever get a truly pure semiconductor. So we do have some little items floating around. We do have some electrons floating around in there, and we call those minority carriers, but there's very, very few. So what we do, we don't draw little circles all the time. And I want you to understand, to represent the holes, what we do is they act like, even though they're not charged, they act like positive charge. So normally when you see this drawn, they'll come over here in the P material, and then they'll put a bunch of plus signs in there. Now, if I come over here and take another material, and then I dope it with a pentavalent, then what we end up in a crystal drawing like this is we end up with what? I'll come over here on one side, and instead of having 2 little electrons, I have what? 3. So now instead of having 8 out here, the dang thing has 9. What does it want to do? Spinning out there. It don't like that 9th one out there, so what will it do? It'll release it. So these electrons are just floating around inside that lattice, just like the holes. They're just floating around inside the lattice, waiting to be what? Waiting to be moved. So we come over an N material, which I'll represent with a bunch of symbols for electrons. So we use plus, not that it has a plus polarity, but it represents the absence of electron, and it represents a hole, and the minus symbol represents the extra electron. So that would be more correct, right? You understand? But the N material still does not carry a charge. Y'all understand that? Because the protons and the protons and the electrons inside the crystal still match. The only way you can have a crystal or something get a charge if you kick the electrons out completely, and then you get what we call an electrostatic charge. And of course, if I come over here and put a DC voltage source across here, along with a resistor, then what's this guy going to do? This is going to push the electrons, and then the positive charge is going to pull them in, right? You understand that? So now we have current flow. So what happens as soon as I dope these semiconductors, the opposition goes down. So now we got a lot of majority carriers, and the opposition goes real low. So an N region, by the way, an N region is also called, an N material is also called it's called a donator. And then a P material is called an acceptor. TER. Because the donator wants to donate electrons, right? And the P material wants to accept them. That's two other terms you'll hear on the test. So this is another name for P and N. So what's going to happen is when we do this fourth step down here, is when we do what? When we fuse those two things together. We form a point of contact, is referred to as a p-n junction, and this is electrons. This is semiconductors, is that p-n junction. And we'll look at the first use of a p-n junction in a device called a diode. That's our first device. We talked a little bit about that. A diode is a device that only lets current flow in one direction. So it blocks the current flow in a direction. We call that reverse bias. And it allows current to flow in one direction. The direction we allow it to flow in, we refer to that as forward bias. So the p-n junction, I had the book out there, and you can look at it. So what happens is when we come up here and we fuse these two things together, and my slides are not what I want, but we'll make do. So what's going to happen, which is explained on the next slide, is when I come up here and put these things together, we form what's referred to as a p-n junction. Of course, we'll draw it like this, where I'll come over here and put a P material over here. So we got a bunch of little holes over here, right? And then I'm going to come over here and fuse that with another one right here. This is going to be an N. This little place right here, this is referred to as a p-n junction. So I don't have any power on this thing at all. I don't have any voltage on it, but what you can see what's going to happen. What's going to happen? I got all these electrons over here looking for holes. I got all these holes over here looking for electrons. So what's going to happen right at these junctions is these electrons are going to jump into the holes, right? You understand? Now what's going to happen is these guys right here is going to be, right in here, it's going to become depleted of majority carriers. When that gets out so far, then your electrons cannot move over to the holes, and the holes cannot accept any more electrons. And this right here is technically called the depletion region. And that's the way it'll say. Now what this does, it creates a charge across the junction. And it ends up creating a little battery in there that sets like that. Now it doesn't have any, the silicon and the depletion region has so much opposition right now, is that it can't produce any current, but we can measure with our meter. Our meter has about 10 megohms worth of resistance on it. So we can measure this voltage, and we refer to this as the barrier voltage. Let me find one of my meters. diode. And to measure this, what we're going to do, I'm going to come over here and put my black lead on this guy right here. And I'm going to come over here and put my red lead on this guy right here. And we'll be able to measure the voltage. You can't do it on the voltage scale, Bobby. We have a special scale that we'll talk about later on. My camera's set up. By the way, the symbol for this junction is going to be, this is in your textbook, is we come over here and we draw an arrowhead. And it's supposed to be filled in, but a lot of people don't do that. And then we put a bar. And this is the symbol for a device called a diode. So in schematics, this is what we would represent this device as. This end right here, this bar right here, this is called a cathode. And then the arrowhead is referred to as the anode. So somehow they identify this. When I come in and look at the device, somehow they're going to have to identify which is the cathode and which is the anode. These come in all shapes and sizes that we'll look at as we go along. Somewhere on that device, they identify what is what. Let's see if we can get it to focus in on this. But I'll pass one of these around and you can look at it. Then, okay, it won't focus in on it. Come on, come on, come on. There you go. Can you see it focus in there for a second? So I don't move it. So we notice on one side, you can almost see it. There's a ring. There we go. See the ring right there? That identifies the bar, that identifies the cathode. So what that means is this end right here is the cathode, and this wire, this lead right here is the anode. Are we okay? And I can bring up tons of these. Yeah, I focused in for a second. There we go. That's good. See the stripe around the end? And so what I'm going to do is we check these things all the time. So see right here, can y'all see this on my meter? What's that a symbol for? That's a symbol for a diode. So if we're going to measure this barrier voltage, then what we have to do is we put our meter over on what we call the diode scale. We'll talk more about that as we go along. And then what I'm going to do is I'm going to take my negative lead, my black lead, and put it on the cathode. And I'm going to take my red lead and put it on the anode. That's not good. It's reading me. Oh, let me get another meter. My battery's sticking. That's the problem. So if you look at your meter, which y'all are supposed to have, you should see that little symbol of the diode on there. So this is another meter. And right here, there it is. We use this to set. We use this to check for continuity. What's that term mean? Continuity. No, has not. What does continuity mean? In electricity or electronics, what does the term continuity mean? Come on, come on, come on. It means there's little or no resistance between 2 points. and that's measured between here and here. So wherever you put this at, if it measures continuity, it's going to measure little or no resistance. Usually, we do that so many times to check fuses. So how much opposition should a fuse have? A lot or none? Huh? No, pretty dang close to none. It's got to have some, right? So we use it to check fuses. So a fuse should have continuity. We use it to check circuit breakers. We use it to check wires. We use it to check for opens. So what meters have is they have a continuity checker, which means instead of me looking at the meter, it does that. So if I see that, it means I have little or no resistance between the 2 points that I've got my meter lead at, right? So when I go across a fuse, it should beep at me. If it don't beep, the fuse is what? Bad. If I go across a circuit breaker when it's closed and it don't beep at me, it means the circuit breaker is what? Bad. And it makes checking these devices that are supposed to make continuity real easy. It is also what we use. The same scale on just about every meter is what we use to check diodes. What do I do with my diode? Now this is another diode, but you should, if it focuses in on it, you should still be able to see it. So you can already see the ring on this one. See the black right there? There's the ring. So what I'm going to do is I'm going to take my black lead and put it toward that ring, the cathode. I'm going to take my red lead and put it toward the anode, and we should be able to measure that barrier voltage. So that's about 615 millivolts. Now look what happens when I put my black lead on the anode and my red lead on the cathode. Measures an overload, right? You understand that? So you just learned how to check a diode. It checks the diode real fast. When you put your black lead on the cathode and the anode, for this type, it'll measure around 7/10, 6/10 of a volt. If it measures 0, you throw the diode away. If it measures more than that, you throw the diode away. Very easy to check. And that's why it's got the diode scale on it. I mean the diode symbol on it. We don't use it to check. We use it to check diodes, but that's not exactly true. We use it to check P-N junction. So anything that's got a P-N junction in it, we can check with that meter just like that, which is a lot of stuff. SCRs, FETs, JFETs, and BJTs, and of course diodes. And we have all different types of diodes. Right now we're looking at a regular rectifier diode, which is a diode that's designed to do what? Convert AC into DC. So what's going to happen? So what happens when I come over here and put that black lead right there? That puts a negative potential. So my meter actually puts out a negative potential, and this puts out a positive potential. Well, what's this going to do? What's that going to do to the electron? Negative, negative, what's it going to do? Is it going to attract them or repel them? Negative to negative. Repel them. So that causes these electrons to start moving toward the junction. Positive, positive, what's it going to do to the holes? That's going to cause the holes to start moving toward the junction. And so now what's going to happen is we're going to, as soon as we defeat that barrier potential, then those electrons are going to be able to jump over there, right? You understand? And then the holes are going to be, and the electrons are going to combine with the holes, and now we have current flow. But this is what kind of current flow we have. On this side, we have what? Holes. On this side, we have electrons, which is very interesting. So inside a semiconductor, we got holes. Inside the wire right here, we have, inside this wire, we have both electron and holes flowing inside the wire. It's just this is where we picked up the hole. So what happens is when I put a potential across a wire, then it pushes electrons this way. Well, every time an electron moves out, a hole exists, right? You understand? For just something that we can't understand, because as soon as the hole exists, then the electron falls into it. So electrons are flowing negative to positive, but holes inside the conductor are flowing what? Positive to negative. Now inside this p-n junction, inside this guy, we got what? We got hole flow and we got electron flow. Okay, what do you need? Yeah, I know, but I don't have a fuss at it. Hopefully she's gone home. All right. Yeah, I remember. Yeah, you was in the robotics class. Huh? Yeah, I remember. So that means if I was to come over here and put this p-n junction in an electric circuit right here, right? Now you're gonna have to once you exceed that 7/10 of a volt, anything below 7/10 of a volt for silicon is considered to be a short circuit. So if I was to come over here and do this, so if this is my N over here and this is my P, if I was to come over here and put that, something's gonna blow up. Either the diode's gonna give up, somebody's gonna give up the ghost, right? So anytime we forward bias this thing, we got to make sure we protect it. So we're gonna have to put a resistor in there. And of course, we'll talk about this later on. And as soon as I do that, as soon as it's negative, if this is over 7/10 of a volt, then that causes this diode to start conducting. Okay. So electrons are flowing this way, holes are flowing that way. Outside, we'll use predominantly electron flow. This guy, if this is 5 volts, if I measure this across this diode, we would get approximately what? 7/10, and 7/10 is an approximation. That's not a precise thing. And this resistor right here would measure 4.3 volts because it's a series circuit. But if I increase this to 10 volts, then the diode is going to drop about 7/10, and then my resistor would end up dropping about 9.7, 9.3. Are we okay? Pretty neat. Well, what's going to happen when I come over here and reverse if I come up here and reverse this DC source? Can you visualize what's going to happen? So think of the P. So I'm going to come over here and I'm going to put the negative toward here. And I'm going to put the positive toward there. What's going to happen? So here's an N, here's a positive. This is going to start sucking electrons out this way. It's going to make the barrier voltage bigger. This is going to come over here and start sucking the holes out and make this barrier bigger. And after a time that we can't even understand, there's no path anywhere for anything to flow. So the thing stops. You understand that? So if I put the negative toward the P and the positive toward the N, so the negative toward the negative, so don't get this confused. So I don't come over here, I don't put negative here, and I don't put positive there. I'm saying putting the negative toward, right? You understand? Yes or no? We'll look at that in a minute. So if I put the negative toward the N and the positive toward the P, right? So that would be like this. And then we have to have a resistor right now, right? Or something to limit the current. This is referred to as forward bias. Now what bias is the DC voltage that we apply to a semiconductor to control how it operates. So if that's called forward bias, what would this guy be called? Now, but to get it to forward bias, we have to exceed the barrier voltage, right? Y'all understand that? Yes or no? That makes sense. Are we okay? I don't want to lose anybody. This is the basics of a p-n junction. We have p-n junctions in SCRs, we have p-n junctions in triacs, we have p-n junctions in diacs, we have p-n junctions in JFETs, we have p-n junctions in transistors. So if we don't understand the p-n junction, and we don't understand forward bias and reverse bias, and we got problems. So if we forward bias it, it causes the junction to conduct. If we reverse bias it, it causes it to what? To oppose or stop conducting. It is a switch. That's what it is. But instead of me getting up there and going over and closing and opening the switch, this switch is switched electronically. So it's not switched by a person, it's switched by a bias voltage. Y'all understand? So if I was to put this into an AC circuit, what would it cause to happen? Well, one alternation, it would be forward bias. The other alternation, it would be what? Reverse bias. So it only let one alternation come through. If I only let one alternation come through and it never changes polarity, then we no longer have AC, we have DC. Now it's not pretty DC, and we'll look at that before long. We call it pulsating DC, but it is DC. A DC motor would run off of it fine. They don't care. DC motors look at it as an average. They don't care if it's pulsing or not, as long as it's pulsing at a rate that it can average it out, right? You understand? So what we would do to forward bias it, we put the N toward the cathode and we put the positive toward the anode. So that would be the technique. We use these things in logic. So there's some logic gates we can make. We can make OR gates with them. We can make AND gates with them. And of course, rectifier, we call those small signal diodes though. So this symbol is used for two types of diodes. This is used for a diode we refer to as a rectifier. And it's also used for a diode we call a small signal diode. So a rectifier diode is basically designed, it's usually low frequency because the predominant frequency, power frequencies all over the world, you've got one or two frequencies being produced as far as transmission. We got 60 cycles and 50 cycles. Over here we're predominantly 60 cycles, which in the name of game, it's not an extremely high frequency. Rectifier diodes are not designed to switch extremely fast. They're designed to take AC and convert it to DC. So they're more concerned with giving you a current, right? A pretty good deal of current. Small signal diodes they switch real fast, but they're not designed technically to be rectifiers. Even if you can use them, it's just that they're designed to handle real small signals. So we're talking about very low currents, right? You understand? So if you get into logic, when you take digital, these are the guys we would use to make NOR gates out of and OR gates and stuff like that, because they're not designed to handle a lot of current, but we want them to switch real fast. Rectifier diodes, they don't need to switch real fast, right? You understand that? But they do need to handle current because they're our power supply. The p-n junction is really neat. This is our check valve of electronics. Tubes used to do it, which is pretty neat. Tubes worked off an electrostatic charge. Vacuum tubes had to be heated to cause them to work. So if you've ever involved in vacuum tubes, you'll see a little orange glow in there where they heat the cathode. So they literally have to heat the cathode to make it work. And it has to be done in almost a total vacuum. Usually the tube is made out of glass. So solid state, this is where the term solid state came into play. These are solids. Semiconductors are solids. So they're not made out of glass, right? You understand? If you drop a semiconductor, what's it going to hurt? So here's a semiconductor. That's solid state. It doesn't hurt it at all. No, wait, that's a transistor. And that one is bad. No, that's not a transistor. This is an integrated circuit. This is actually a voltage regulator. We'll get him later. At the instant the junction is formed, some electrons jump over into the P region. The electrons recombine with holes. This leaves holes in the N region. This causes the P-N junction to become electrically neutral. Not the junction. The depletion region is neutral. It don't have any charge. It's on the outside there that builds up that barrier voltage, right? You understand? The area on both sides of the junction become depleted in majority pairs. This region is referred to as the depletion region. So what we got to do is we got to push electrons through that depletion region. So what's happening when you get that voltage up, it overrides that barrier potential and you push them electrons right through there. So this is showing you, this is not in your book. This is out of another book of Floyd. And I know what's going on. I think there were two versions of it out there. Come to think about it. This is a lot like as this I added some more. So what's doping? Trivalent or pentavalent electrons to semiconductor crystal and lattice. And of course the N material is doped with a pentavalent atom, a pentavalent atoms, and then P is doped with trivalent atoms, and then we form our junction, right? And then this is where we're at now. This is covered in the book pretty well. So what happens is we create a P-N junction, and this is not in the textbook. This came out of Floyd, the book we used to teach it out of. That book carried us from DC all the way through solid state, and it was around $300. So we got rid of this guy because we got to the point where we had a lot of students that wasn't taking solid state because they were in the AUT degree, and it just didn't make sense for them to require them. So that's why we split the books back out. Are we okay with this? That's a good picture. The presence of the positive and negative ions on the opposite side of the junction creates a barrier across the depletion region. The barrier voltage. When we look at the data sheets, so understanding the data sheets for these solid state devices helps you out a lot on how they operate and why. But when we look at the VF, this is going to be identified as the VF. It's called the forward voltage drop or the forward breakover voltage. This is going to be VF in your data sheet. And this is the amount of voltage necessary to move the electrons through the electric field formed in the junction. For silicon, it's approximately 0.7, and germanium is approximately 0.3. Now, it does not remain constant, but it stays around. So this thing will start breaking over around 5/10, gets up into pretty good conduction around 7/10. Then when you keep conducting, you put more current through it, the VF is going to go up a little bit, right? And less current is going to vary, but it's not going to vary very, very much. In fact, we had our flashlights at US Steel, they ran off D-side batteries. And we had tons of radio controlled cranes and stuff like that, and they ran off a little NiCad battery, and the NiCad batteries only put out 1.2 volts per day. So what would happen if you went over to 2 NiCad batteries? They were a lot smaller. Your flashlight was real bright. Real dim. If you use 3 of them, you get 3.6 volts instead of 3 volts, and it got real bright. And if you bumped it up against something, it would glow. So how do we compensate for that? We put a diode in series before it biased. And when it dropped that 7/10 of a volt, right, it went back down to 3 volts, and now the thing worked okay. Now what was nice about our flashlights now is they were rechargeable. So instead of us trying to get batteries all the time, what we would do is that every night before we left, we'd hook them up to our chargers, and then we'd go. The next day we come in, we plug them in, we have a real nice flashlight That wouldn't blow when you drop it. So just that 7/10 of a volt of a silicon. The other one we have is germanium. Germanium is about 3/10 of a volt. By far, the most widely used semiconductor is silicon. We now only run into germanium in special applications. Originally, the semiconductors were germanium, but they figured out that silicon, even though it drops a little higher voltage, it has better temperature characteristics. And we don't need that one. Forward bias is the condition that permits current to flow through the junction. And what do? We put the negatives, the potential of the source toward the cathode, and we put the positive potential toward the anode. We never connect the negative to the cathode and the positive to the anode because now we got a closed switch, right? You understand? When the diode is forward biased, it acts like a closed switch. Now a closed switch drops 0 volts. A diode will drop about 7/10 for silicon and about 3/10 for germanium. So if I close a switch across a DC source, we have a short circuit. And that would be exactly what you would get with a diode. So we don't put the negative on the cathode, and we don't put we may put the positive on the anode. It depends on what our common is. But we never put the DC source across the diode. Everybody understand that? So that you'll never hear me say make the cathode negative and the anode positive. I'll say that the cathode's going to be less positive than the anode, or the anode's got to be less negative than the cathode. Reverse bias, this guy acts like an open switch. Prevents current flow through the junction. Is there current flow through the diode? Yes, there's a path through there, right? But you understand, if you understand, is there current flow in an insulator? Yes. We call it voltmetric current. It's so dang, if you put a voltage potential across something, and there is a path through that something, and it does not have infinite resistance, then there will be current flow. It's just that the current flow through the insulator is so small, we can't even think about measuring. You know, you're talking about down in the picoamps, but there's current flow through the insulator. So is there current flow, when this guy is for reverse bias, is there current flow through the diode? Yes, there is. And it's got a name. It's called leakage current. So leakage current is the current flow through the diode when it's reverse bias. And unfortunately, leakage current varies with temperature. So the hotter you make the junction, the more leakage current you have. The colder you make it, the less leakage current. So this is why solid state devices are kept cool. You cool them down, right? They have a temperature of operation. Old vacuum tubes, we wanted them suckers to operate hot, but there's a lot of people that got burned on vacuum tubes because they operated off it. Semiconductors don't like a lot of it. That's why you hear these fans and everything running over here on these things. That's why your laptops have fans. That's why even your tablets have some way to cool that processor off. Forward bias permits current flow. Acts like, it don't say it is a closed switch, it says it acts like. How much voltage does a closed switch drop? If it's good? None. We can't measure because there's almost zero resistance if the switch is good. But this guy here has that VF we have to come to, right? Negative terminal of DC is connected toward the end material. This pushes the electrons toward the junction. The positive terminal in DC supply is connected toward the P region. This pushes the holes in the P material toward the junction and pulls the electrons away. So we have current flow inside the junction. In the P material is hole flows, and the N material is electron flow. So this is showing, I got a resistor. What size resistor is that? Nobody knows. 2 seconds. Good, crazy. So green is what? 5, blue is 6, and then brown 560 ohms. Plus or minus 5%. By the way, in this class, if you come up and say, Rich, I need a 1K resistor, what's the next thing I'm going to say? What's the color? What's the color code? And it's something you need to know without using the chart. I don't know if some of y'all remember it, but there was before ITD Tech, there was another hardware called Retz Electronics. And they didn't teach color code. They let them buy the Radio Shack sold this little color wheel, had these little rotating things on there. And you could line up the color, and then across the top you would read the number. And we had an employer call him. And he brought that up right off the bat. He said, don't you send somebody out here that's got to use that color wheel to do a resistor. Because this is one of the basis of your trade, is understanding resistor color code. So notice the biases thing, we use a DC source. So bias is a DC source that we apply to a semiconductor to set its operating parameters. So all your solid state devices have to be biased. So that means if I do the symbol for a DC source, a lot of people come up here and say, this is a symbol of a battery, and that is true, but it's also the symbol of a DC source. Then I would put in that direction right there. And then I would have current flow, right? As long as my battery put out something that was greater than 7/10 of a volt. As soon as I'm greater than about 7/10 of a volt, then we have current flow through the diode, and then we have current flow through the resistor. Now, current flow through the resistor, we use electron flow, right? So if this was 10 volts, then what would I measure across the resistor? About what? What's that? This was 10 volts. Series circuit, Kirchhoff's voltage law says the sums of the voltage drop in a series loop have to equal to the applied voltage. If this drive is dropping around 7/10 of a volt, then over here I'd have 9.3 volts. And that's the difference in semiconductors. So semiconductors, when they're turned on, you'll never get the entire voltage. A semiconductor will always drop a voltage, even bipolar transistors. But now instead of me coming over here and turning this thing on, we can turn it on with a voltage. And I can turn it off by simply doing what? Switching the polarity of the battery. Now I'm switching the polarity of the battery. You say, what good is that? But remember AC. The positive alternation has a DC average. Negative alternation has a DC average. So that means one of the alternations on an AC signal is going to forward bias this thing. And then the other alternation is going to do what? It's going to reverse bias. Which is real neat. And we call that rectification. Forward current flow. Once electron enters the P region and combine with the holes, they are valence electrons and move from hole to hole until they reach the positive source. The P region, the holes are produced in the opposite direction of electrons. Therefore, the majority of carriers is produced current toward the junction, right? We already said that. This is what we got here. And when does this occur? This occurs as soon as we exceed the barrier potential. So that's a nice illustration. So in P material, the majority carriers are holes. And in material, the majority of carriers are electrons. Any questions so far? Yes, no. Y'all got all this thing? Or is it too hard right now? Pretty straightforward. And these guys, what determines the physical size? The physical size of the diode is determined by how much current flows through it. I mean, it is a current valve, right? You understand that? It's a check valve. What determines the size of a check valve in fluid power is how much flow you want to go through. So we have these diodes right here. Let me pass these around. These are two. And y'all should be able to see the cathode. And this is a diode. It's a stud mount diode. They call it a pigtail. Now this diode's big enough for them to put the symbol on it. See the little diode symbol right there? So this is the cathode and this is the anode on this one. If I want to check this with my meter, I'll come over here and I got it on the diode scale. Wait, Rich, this thing's big. Well, it's a diode, right? You understand that? Now the VF is going to be smaller on this one. It's still a silicon diode. But this is going to be smaller because it's got a lot of majority carriers in there. They're heavily doped. But here's the cathode. I'm going to put my black lead out here. I'm going to put my red lead right there. And there's the forward voltage drop right there. I come over here and reverse that. My meter shows overload. I come over here and put forward bias. My meter shows the junction. So basically, it don't make any difference how big the device is. If it's silicon, you're going to be able to do it. Now this measure, so that 7/10 of a volt, this is not germanium, this is silicon. But the problem is, it's got so many, it's heavily doped, so it means it's got a lot of silicon in there. It's got a lot of majority carriers because this guy here is rated, I think about 60 amps. So that's the diode. Could also be used as a weapon. Yeah. You know, Charles Bronson in Death Wish, he used a sock full of quarters. That would have probably been better. The depletion region opposes forward bias. The negative ions near the junction in the P region try to prevent the electrons from moving. But as soon as we exceed that barrier voltage, as soon as the external voltage overcomes that barrier voltage, this sucker just avalanches. But it always drops at 7/10 of a volt. So these guys still have to be heat sinked and stuff like that. You know, you think 7/10 of a volt, that's not much. You know, but if you're conducting 1,000 amps of current, 7/10 of a volt is still 700 watts, right? You understand that? That thing would get really dang hot. So we usually have to mount those things on heat sinks. What are heat sinks? What we're trying to do in our semiconductor material is we're trying to make our semiconductors as small as we possibly can make them. Well, what determines how much heat that junction can get rid of is how much air is exposed to, right? So we have these big old metal plates. They have fins all over them that we mount these devices on, and that's exactly what they do. They create a lot of surface area to dissipate that heat. We call those metal plates heat sinks. And I think we've even got some inside our trainer. This is Scott, by the way. What's your last name, Scott? Yeah, he's a returning student. How long you been gone? Yeah. A conduction occurs at approximately 7/10 of a volt for silicon. Now notice we say approximately. How do you know? Well, we got a data sheet we'll look up and it'll give us the average VF and then it'll give us the maximum VF. So it gives us the maximum VF, which would be the voltage, the the diode will drop when you're running at its maximum current. Everybody understand that? The VF, the other VF they give you is going to be a typical VF. They'll call it VF average, and this is going to be what it should average out. But you got to understand is the current goes up, that is not a conductor, it's a semiconductor. It's been doped to be more conductive, but it still has some opposition. So as the current goes up, the 0.7 of a volt is going to go up, right? It's going to go up, and if it goes down, it's going to come down. So if we look at the forward bias curve on a diode, what we would see is it starts off conducting a little bit because there's a path. And then right around for silicon, right around 0.5, it would start kneeing. And then what would happen is it would shoot up like this, but it's going to be at an angle. And this would be IF, the forward current, and this would be VF right here. So this goes up at it goes up at an angle. So that VF increases just a little bit over the range of operation because it is not a conductor, right? You understand? So even when it's forward biased, it has some resistance. If I put current through resistance, it's going to do what? It's going to drop the voltage above the variable. So this is basically what it looks like. These little old resistors are little old tiny things, right? You understand? But what this happens, that little resistor in there causes so the sums of the voltage drops would be the 0.7 plus the voltage these little old tiny resistors drop. And like I said, they're very, very small. So I think this diode right here, I think it's a 1 amp diode, and the maximum VF would be 1.1 volt, which is what, less than 400 millivolts over the 0.7 of a volt, and that's over its entire range, and that's at 1 amp. If you run over 1 amp, then what could happen is you could burn the thing up, right? Understand? So that is not exact. So this is basically, I've already done this. So when we put this in a circuit, which we're not, and we've done this with a meter, right? Here they've got an ammeter. So what we're going to do, by the way, is we're going to develop this curve right here. One of the first labs you're going to do is develop this curve. So what you're going to do is you're going to take the diode, you're going to forward bias it, you're going to put it in a resistor. Now, what's nice about putting a resistor in series is you don't have to measure current. You can calculate current. So what you're going to do is you're going to put your resistor across, you're going to put your meter across the resistor, you're going to measure the voltage. You're going to say I is equal to what? V over R, and then you're going to record that in a chart. And then you're going to come up and set up this VI character. We call this a VI characteristic curve. Y'all understand why? So the vertical axis is the what? The current, and then the horizontal axis is the voltage that causes that current to flow. And you'll see it does this. You can actually see it. Do this little slope right here. You start going up, and you see when it starts conducting. Of course, if you put a potential across that, there's going to be a real small current flow through it, right? To understand. So that's when I draw mine. Notice I started off just having just a tiny bit of current, and then when it hits this, we call this the knee, by the way. Why do we call that the knee? Because it looks like a knee, right? As soon as it hits that knee, then it starts conducting a lot. And then the voltage drop across it varies a small bit depending on the current. Oh, going the wrong way. A reverse bias prevents current flow. It acts like an open switch. Is there current flow through it? Yes, there's a path. And what do we call that current? I need to make sure I put that in the philosophy. We call it leakage current. What controls the amount of leakage current? Temperature. So we'll see this. We'll do this on purpose. We're going to deliberately break this diode over in the reverse direction. That doesn't sound good. Fine. Can I help y'all? Okay. So prevents current flow, acts like an open switch. The negative terminal is connected toward the P region. The positive terminal is connected toward the N region. This pulls electrons away from the junction and makes the barrier region bigger. So the more the barrier region, the bigger the barrier region, the more opposition it has, right? Okay. Now the problem is though, if I can put a high enough voltage across this thing, I can cause it to break over in the reverse bias direction, which don't sound good because it's not. The depletion region is widened until the potential difference across matches the external voltage. When the diode is reverse biased, the depletion region acts like a capacitor. Remember from DC, didn't y'all talk about a little about capacitors from DC? Y'all get that far? But no, a capacitor is a neat little thing. It has the ability to store energy. It stores it electrostatic, which is really good. The internal capacitance is called the depletion region capacitance. I don't even think that's in the book, so let's don't worry about that. So this is reverse bias, right? The depletion region gets what? Bigger. By the way, the resistor, so let's say I come over here and I've got a 10K resistor right here. And over here I've got a power supply. So I've got the negative pointing toward the end. And let's say this is 10 volts. What would be the voltage drop across the resistor? Huh? So 10 volts, is that correct? How many agree with 10 volts? So first of all, we got to look at, and this is why understanding Ohm's law. Understanding Ohm's law. V is equal to I times R. So the amount of voltage drop I have across that resistor is dependent on the amount of current flow I have through it. The diode is reverse bias, right? So that would be like me going over there and turning off the light switch and measuring 120 volts across these bulbs right there. If I turn that light switch off, would I measure 120 volts right there? What would I measure? Guys, what do I measure? It's reverse bias. How much current flow we got? We got leakage current. It's in the picoamps, which we can't. Our meter don't measure that. Our meter don't even come to that. So what's going to be measured across the resistor? 0. Yeah. So this guy here is going to measure 0 volts. What are we going to measure across the diode? And I'll put in there, I say, what would be measured across the silicon diode? And guess what somebody's going to say in this class? It's so small. Somebody's going to say 7/10. It's reverse bias. It's acting like an open switch. What do we measure across an open element in a series circuit? Not across an open element in a series circuit. We measure the applied voltage. You say, well, what about that resistor? To get voltage drop across a resistor, it's got to have current flow through it. So the resistor's not dropping any voltage. If the resistor's not dropping any voltage, that's basically taking this negative and putting it right there, and that's taking this positive and putting it right there. There's nothing in the circuit dropping any voltage. So my diode would measure the applied voltage when it's reverse bias. But I guarantee you somebody's going to, in this class, I'm going to put a silicon diode and somebody's going to say 7/10. Or they're going to come over here on this resistor and they're going to say it's going to drop 7/10 of a volt, or they're going to say it's going to drop 9.3. So they're not paying any attention on is it forward bias or is it reverse bias. Somebody in this class is going to do that. I have never taught a class where somebody didn't get that confused. So prove me wrong, please. Please. Even if this is a small class, somebody's going to do it. Guarantee. I hate to say that. Reverse biasing a diode causes the current to become practically zero. However, there is a small amount of current that is produced by minority carriers, which we call leakage current. This current is usually in the micro or nanoamp range, and we just ignore it. But we do have to worry about it if we get it real hot, right? So what you're going to find out about semiconductors, they give you an operating temperature. As long as you maintain within those operating temperatures, you're going to be okay. If you get above it, then what's going to happen? The leakage current gets up high, P is equal to I times V, V is equal to I times V. Leakage current goes up, diode's dropping voltage, power goes up, it gets hotter, right? You understand? Which causes the leakage current to go up, which causes the power to go up, which causes the leakage. So we get to a point where this thing's going to avalanche just strictly by temperature. And we'll cause that to happen. So this is reverse bias. Okay? Okay, guys, y'all take a break. We'll look at some data sheets real quick in a minute. The current is usually in microamps or nanoamps, and it's called IR on the data sheet. The reverse bias current depends on the junction temperature, not on the amount of reverse bias voltage. We talked about that too, right? And this is showing you. Reverse breakover occurs when enough reverse bias voltage is applied. The voltage must be high enough to accelerate one electron toward the positive end of the p-n junction. During the travel, this electron bumps into another one, knocks them out, and it just avalanches. Now the problem is all of a sudden we got a lot of current flowing through the diode in the reverse direction, and the diode is dropping a lot of voltage. So V times I is power, right? You understand that? Reverse voltage that causes the avalanche is referred to as the reverse breakover voltage, or the breakover voltage in data sheets. Just about all textbooks that I've seen, for some reason, they don't call it the reverse breakover voltage. Your data sheets don't call it this, but your books do. And this book does the same thing. They refer to it as the peak inverse voltage. Or PIV. But I've never seen a diode data sheet with a PIV rating. The grading they call it the maximum reverse breakover voltage, repetitive breakover voltage. We do have diodes that can handle a lot, but not consecutively, right? You understand that? Are we okay? And this, if you a regular diode, a regular p-n junction diode, if you break that sucker over in the reverse bias direction, it probably a 99% chance it's going to be negative. It's not going to act like a diode. It might start acting like a resistor. Another problem we have with semiconductors is that they'll fuse and they'll start acting like another. So semiconductors, when they go bad, they can open, or they can short, or they can become what we call leaky, which means they conduct current when they're not supposed to. You understand that? If diodes get hot, yeah, they do get hot. They drop a voltage even before it drives bias direction, right? This little 1 amp diode won't, because 1 amp is 7 volts. That's only 700 millivolts. That's about 1 watt. I don't think you can figure it. It might be. A single p-n junction is called a diode. We have two categories of diodes. Regular diodes. Now we have other special diodes that we're going to talk about. They have another name that goes with it. We have a Zener diode. We have a tunnel diode. We have a PIN diode, a PIN diode. Those have different names, right? If we use the term diode, we're talking about just a device that has a single p-n junction. A light emitting diode, LED, light emitting diode. So these are special diodes. A diode is either has the same signal, whether it's a small signal, unfortunately, or a rectifier diode. This is the symbol for this diode. And it's supposed to be colored in, but you'll see it a lot of times drawn like that because it's real easy. Over in Europe, a lot of times they draw it like this. So they put a line all the way through. So they do this, and then basically they come and draw the symbol like that. So that's another symbol you'll see for the diode, especially if the symbols, the schematics were drawn over in Germany or something like that. Very common. So a single PN junction is called a diode. We have two categories of these. We have rectifier diodes and signal diodes. The rectifier diode is designed to rectify 60 cycle or 50 cycle AC. You get into switching power supplies where it gets up around 15,000, and you have to have a high frequency rectifier diode, a special type diode. These guys are designed for around 50, 60 hertz. The amount of capacitance they have. Your small signal diodes have very small capacitance because they take a lot less energy, right? You understand that? But they're designed to work as signals. Even though I have seen them use rectifiers, but they'll be down in the very small milliamp range that these guys can do. Are we okay? So what a VI characteristic curve actually looks like, if I can find my blank page that I stuck in here. Which, no, I'm not, because I told it not to save it. So let's put another blank page on here that I can draw on. So we have what we call the forward direction, the forward bias direction. So what the VI characteristic curve is going to look like. So this is I. And this is IF forward biased, and this is IF reverse biased, right? And this is VF right here, and we call this VR, so that's voltage reverse biased. So what would happen is we start off like this, and we get a real small current flowing through it because there's a path through there. And then when we get up around 4/10, 5/10, it's going to start kneeing. And then it's going to go up. It's not going to be quite vertical. It's going to have a slight slant from it. Now when we get on this side over here, what's going to happen? It's going to conduct. And then we don't have enough room. I'm going to break that up. And sooner or later, it's going to avalanche over here. This is bad. This is what's going to damage. Now, the diode that we're going to do the little small signal diode because it has a very low VF. It's got a VF of around 80 volts. So break this over. We're going to deliberately break it over, but we're going to put a 10 meg ohm resistor in series. So even when it breaks over, it's not going to hurt it because that 10 meg ohm is going to really limit the current, right? You understand this happening. But we're not going to do that section of the lab as units because it takes about 80, 90 volts to break this thing over, and that needs to be voltage pretty dangerous. So we'll do this as a class. So we'll come in here, we'll hook up about 5 power supplies, we'll pump that thing up, and we'll look across that resistor, and we'll notice when current shoots up and break it. And then we'll get a soldering iron and we'll put it up next to it and we'll see the current goes up. And we'll get the breeze spray and we'll spray them and see the current drop down. So you'll actually see that reverse current vary with temperature. The VF side, where you'll do that as we'll do that. Huh? Huh? I need to call out. I know we got 6 people. And since we only teach it once a year, that's basically why they let us teach it with a small class. Plus they like So what we need to do now, just for the heck of it, no, not for the heck of it. Let's go. Y'all all need to log into Blackboard. And the main section of this course is learning how to read data sheets. If you know how to read data sheets, then you know how to substitute parts. So when you have a part that goes bad, you don't necessarily have to replace it with the same device, right? All you need to do is replace it with a device that's got an equal or better specification. As long as you don't go below the specifications, you're fine. A lot of people don't know that. We had a scale go out at a paper mill down somewhere in Alabama. One of the big paper mills. And, I fixed it. It wasn't a scale, it was a printer. One of the ICs went out, and I didn't have the original one, but I had one that was better. And I replaced it. The thing ran for 5, 6 years. And I got a call one day. They said that they sent that board back in because it failed. They said it had the wrong IC. That was the problem. But that's true story. And I said, Charles, I replaced it with one that was better. And it's been running for 5 years. So, so what we're going to do is look at data sheets. Not handouts, data sheets. So this is pretty important. And we'll look at, this is a small signal diode. This is the one we're going to break over. So let's go ahead and look at the data sheet on this guy. And this is a typical data sheet. So first of all, this shows us the different packages you can buy this thing. Now what we start off with, number one, in semiconductor data sheets, what we'll find is the first table we see is something called the absolute maximum rating. Now what the absolute maximum ratings are, they do not guarantee operation. They guarantee the device will not be damaged. There's a big difference, right? See how the device operates. So this is where the breakover voltage is going to be. So right here, VRRM, the maximum repetitive breakover voltage. So this diode right here won't break over. So we don't break it over at 90 volts. I was wrong. I think it breaks over 100. So it means I can reverse bias this little diode and it doesn't break over. It's guaranteed to not break up. This is guaranteed, right? You understand that? That means it's not going to break over at 100 volts. Because it's impossible for them to make two of them exactly the same. But every one they make is guaranteed to not break over at 100 volts, right? It's just like the RPM gauge on a car. You know, if you got an RPM gauge, it used to be in a red line. When that car hit that red line, it didn't need to come apart. But now it's got a chance of blowing up, right? It could blow up at the red line, but very seldom it is. Non-peak forward surge current. So this guy here could handle up to 4 amps for 1 microsecond, which is not very long. Then down here, this is the actual operating characteristics. So the VF of this diode, notice they give us several VFs. They say, okay, at 5 milliamps, it's going to measure. Now notice they give a minimum and a maximum. So what that means is that we know it's going to break at least 0.6 of a volt up to what? 720 millivolts is where it's going to conduct. All the way up to 100 milliamps, well, up to 100 milliamps, which is what the diode is rated at, then that's going to be, it's going to drop about 1 volt. So notice it's still close to 700 millivolts. So we're going to use 700 millivolts when we do our calculations because it's always going to be close. And we'll talk about that in a minute. Call it approximation. The leakage current. What's our leakage current? At 20 volts reverse bias, 20 nanoamps. At 20 volts at 150, 50 nanoamps. So you can see the reverse bias doubles with that heat. 75 volts, which is still not a breakover, is going to be about 5 microamps. But guys, we're still talking about what? Microamps and nanoamps, right? You understand that? So for all practical purposes, my meter will not hardly measure, won't measure their nanoamps, right? You understand? It might measure microamps. We'll get to see that. The capacitance, we don't look at that, and the reverse recovery time. This gives us how fast it can switch from off to on, which is not really our concern. So the ones we're really interested in right now is this reverse breakover voltage, this forward voltage, and then the current, and then the actual current it's rated at will be up in the maximum rating table. So where's our forward current at? Yeah, average forward current. So this guy here would be rated at 200 milliamps. Now the 4000 series, notice over here it says 4000X because this gives us several variations of the same diode. So this guy goes all the way from the 4001 to the 4007, and the only thing that varies is their reverse breakover. So 1001 would have a 50 volts. Non-repetitive would be 60 volts. But this guy would be able to handle 50 volts all the time. 60 volts if it's a one-shot deal. Which would give us an RMS value of 35 volts. Everybody understand that? So these, in AC, these are not RMS. These are peak voltages. So that means if I don't understand AC's got peak, and I say, well, this is only 40 volts RMS, well, 40 volts RMS is, divided by 0.707, right? You understand that? So that would be what? 90 volts peak, and that would bottom. So you got to understand, if we put these things on AC, these things block peak. They don't block RMS. They block peak. So that's why if you're dealing with an RMS system, which you're going to deal with an RMS system, right? So when we say 120 volts, that's RMS. If I say a transformer has a 12.6 volt transformer, that's 12.6 volt RMS. But this diode is not going to drop RMS. This diode's got to drop what? VP, right? You understand? Yes or no? So what's nice about this data sheet, it gives you RMS. So that means if I've got this in a circuit that's 40 volts, I can't use it. Even though it says it'll block 60 volts, that's a non-repetitive peak voltage, right? You understand? So what would we use? We'd use 50 volts. So the 4001 has a breakover voltage of 50. The 4002 has a breakover of 100. The 4003 has a breakover of 200. 4004. So what varies with this diode? The only thing that varies is the amount of breakover. So that means I've got a 4001 in my circuit. It fails. I don't have a 4001. I have a 4003. Could I use it? Sure, I could use it. It's got a breakover voltage rated at a lot higher than I need. So it don't hurt to use one that's got a higher rating. It hurts to use one that's got a lower rating, right? So if I've got a 4004, then I wouldn't replace it with a 4001. Right? You understand that? Yes or no? What's the current rating on this thing? Right here, average rectified forward current 1 amp. But look at this guy, a non-repetitive peak current. So for one alternation, this guy could handle up to 30 amps, which is, when we start talking about filtering, this becomes very critical. What else? Operating storage temperature. We don't even need to know that when we stored it. What else? The VF on this diode at maximum instantaneous forward voltage drop. So that means when it's running at 1 amp, it's going to be somewhere between 9/10 and 1.1 volts. The average forward voltage drop on this guy is what? 600 millivolts. I'm going to say 6. It's hard for me to see that. And then the leakage current maximum is what? 10 microamps at 25 degrees centigrade and 50 microamps at 100 degrees centigrade. So see, just reading these things, we get a pretty good feel of what we just got to be talking about, right? Y'all understand that? Okay. Now, of course, we're doing the lab. The lab's going to be hard, so you don't have to have data sheets. But understanding how to read the data sheet, so right off the bat, I know I can replace a 4001 with a 4003, but I couldn't. Is there a 4003 that's up to 4? I think it's up to 4, but I couldn't go down, right? But if I didn't know that, so this has happened in this class, where the lab calls for a 4004. Instead of coming, all I got was 4007, and we got a 12.5 volt supply, 12.6 volt power supply. 4007 has a breakover of what? 1,000 volts, and they're worried about putting 12.6 volt RMS circuit. The lab book calls for this, and I don't have any of these. But see, just understanding that, right? You understand that? So the first lab we'll do in class, and we'll do it probably at the end of class. We'll go to lab. We'll do the second half of the class. Is we're going to do this. You're going to actually develop. We'll talk a little bit more about that. We do have a little problem that power supply will put out less than 1.2 volts. So what electronic device? What do we use to adjust the voltage? We learned about them at Junction. So what we'll do, instead of looking at directly to the output of the power supply, we'll hook it to the output of the Junction. And that way we can adjust it all the way down to 0 if we want to do it all the way up. So we'll have to do that. Now the reverse breakover, we don't have to do that, because this guy, the 914, by the way, you notice diodes start off with 1 in. Just about all of them. It indicates it's got 1 junction. So bipolar transistors are usually 2 in, because the bipolar transistor is 2 in. But of course your FETs are going to be 2 in because they're transistors. The transistors were originally by the bipolar transistor. And they're basically assigned, the number has no reason. These are all JDEC registers. JDEC is Joint Electronic Device Engineering Council. And what they do is they register packages. So they register packages. They assign it a nomenclature, like 1 in or 2 in or something like that. And then they assign whatever number they're on. You understand that? So basically that means that 1 in 914 was created before the 1 in 4001. That makes sense? These are open technology packages. Well, that's not, they're open technology diodes. So if they're open technology, that means anybody out there that makes semiconductors can make a 1 in 914 and not have any problem. And they can make a 1 in 4001. It's open technology. This data sheet is open technology. It's not registered. So if I get my hand on a data sheet, I can engineer a diode that meets the specifications, then I can put the 1 in 40 series on that diode. But we do have some transistors that are diodes that are not they're not open technology. Are we okay? Yes or no? Okay. So what are we fixing to do now? And no, we're not going home. We're fixing to put this